strange ways to do mechanics. You're used to differential equations, solve them, off to the races. That's what we're getting at eventually here, but today I'd like to show the thing that makes it possible to do that, and that is the whole notion of a potential energy. So the idea of this, after a little quick review, which we'll zoom through, is that the force field, or a potential field, can be defined by making the potential energy equal to the kinetic energy of whatever it is that produces the potential. And use no more axioms than we already have. So there's a logical economy associated with all these bouncing ball scenarios. So we'll see that, and I think we've already seen that when we made the mass ratios really high, as we're going to do again today to create a potential, that the collisions happen so quickly that the ball coming up, the big ball coming up, is being pounded by the number 2 mass, so that finally it gets rid of its momentum and then actually starts to be pushed down. And it's that nice, gentle, almost looking, if you didn't look too carefully, like a parabola for your elementary sophomore mechanics of motion in a gravitational field. But remember, all of the stuff that we've been doing up to this point has ignored gravity completely. We're doing all of this in a space shuttle or some gravity-free region. So that's the first time we actually are going to have a force field, or what looks like a force field. We'll have 2 extremes, isothermal, adiabatic. This will review a little bit if you've had some statistical mechanics. Then we're going to go back to the most simple situation involving a really huge mass coming in, trapping a tiny little mass that bounces off of a ceiling or another wall, practically crushing poor little M2s. It's going to be sadistic. But what I'd like to show here is a number of very important phenomena that come up later in advanced classical mechanics, and that's the idea of the conservation or near conservation of what's called action. So we've talked about momentum first, energy second, velocity being a part of both of those, a little bit into the idea of acceleration where velocity changes, but it's been discrete collisions for that. And now here's another quantity that doesn't get as much press and is really quite mysterious, and we'll try to make it less mysterious as we go through this course. But it's just another very important dynamical variable. And then at the end, after we've seen this, what we call the monster mash, I'll show you an interesting wave analogy that is fun. And TC, if you could, at some point, we'll run the bounce it. We'll run the bounce for what you've been already setting up, but also wave it. Bandit can do it too, and I'm talking about the fractals, the quantum carpets. Probably wave it is the best, so you might as well get that one going for when we get to the end of the lecture today. Okay. Now, we've been talking about velocity plots. We've been talking about position plots. Those were part of this discussion where we had a ratio of 49 to 1. It's a monster mash in a sense, just that it's over fairly quickly with a deflection of the large mass by the small one. So this is what I'm talking about, is effectively you can think of this large mass as being in a force field that's caused by a smaller mass. And if the smaller mass is really small and really fast, so that there are many, many collisions, then the result will be indistinguishable from an exact treatment using calculus and potentials, differential equation involving a force field. There's a repulsive force field acting on this ball, and everything we're doing here can give the results that you would get by the conventional methods of solving a differential equation with a force and potential. We need to use this in order to develop with a logical framework of the idea of potential, force, and energy relations. And there will be two types, the adiabatic and the isothermal, that come up in that discussion. So here's the scenario for now. I put everything in a horizontal theater, and I'm imagining a large mass here that's perhaps moving fairly slowly. We'll talk about it moving much more slowly than this one. Certainly you're familiar with the idea, and I think you saw that in the simulations with this thing, and I'm going to put that on this screen now. No sense not making use of this. I will put here so it fits the frame perfectly. In the collisions that are going on here in the vertical setting, in either of these cases, no gravity again. The only forces are between the walls here, floor and ceiling here, and the two masses interacting in a Lagrangian geometry that we by now should be fairly familiar with. So you can see that as the space that's allowed, remember this is time, so the space that's allowed here, that's the minimum space that this thing ever achieves in the progress that we see here. The ball is moving quite fast. The velocity up and down from here to here is as big as it gets, and that right here in the units that we are using here, 0 is right here. This is 1. Let's see if I've got 1, 2, 3, 4, 5, 6, and 7. So basically 7 units of velocity, or a change in 4 by 14 units of velocity is what we have here. And the way you would talk about this in thermodynamics or statistical mechanics to say is, as I reduce the space allowed for this little ball, it's going to get hot. That means it's going to be going fast when you're close, and it's going to be going more slowly when this space is expanded. So the idea of compressing gas, this is the kinetic theory of gases that came up shortly after Newton's ideas became accepted, is the beginning of statistical mechanics and thermodynamics. Now, statistical mechanics, strictly speaking, came quite a few years later, but already people like Boyle and Boyle's law for volume, pressure times volume equal to temperature, and if the temperature is constant, that's a nice hyperbola. We'll have a force law like that coming up here as well. And then we'll have a more complicated force law, we call the adiabatic one, where we conserve energy. We don't have energy coming in and out through somebody wiggling the wall for either one of these two masses. So the idea is that when you are having large distances, the velocity will be less, and on a plot like this, where time is this way, the slope is less than it is here. Here the slope is more, looking at it from this point of view, closer to infinity. The larger, the more horizontal these lines come, the larger the slope or velocity is. Here they're just sort of lazily going back and forth. This one is giving change in momentum each time it hits that mass right there. And we'll suppose that the mass here is only just moving a little bit, you see, so little you really can't see that it's moved at all. It's just got a little bit more momentum each time this thing makes a circuit. So we have a longer time, delta t, between collisions than we do right here. We have more collisions and they're more severe. So this is a double whammy. The idea is that you're going to have shorter times. As you've made the distance shorter, you're going to have less time that the thing has to go to get back and forth to give it more momentum. You also are going to have more velocity. And as you shorten that distance, it's really a triple whammy. There's less time between collisions, no matter what. Yeah.
What is that? Is that delta t?
Delta p.
No, the delta t, the time change.
Oh,
yeah.
Delta t.
Yeah.
Right
what is
here.
that one? Is that the time of collision?
Yeah, it's just the distance that happens to exist right now. The distance that this travels is 2 times. Remember, we used y before because our balls were all vertical, so I'm using that same letter for the distance, right? And the distance out and back, that's this and this, is 2y, okay? And so, assuming the velocity is constant, speed is constant, velocity changes sign perfectly, okay? The time between collisions here is going to be that distance times 2, the y times 2, right? You will see that clearly, and divided by the velocity of the little ball here, okay? So basically the elementary theory of, kinetic theory of gases, which came, as I say, came later than Boyle's law, was based on that type of argument. Actually in 3 dimensions, but 1 dimension is once you've done that, you can do the rest fairly easily. So the force that this thing feels, if we make one more definition, and that is that the force something feels is the change in momentum per time. And we're going to be talking about discrete times, so we'll have discrete changes in momentum each time a collision occurs. And that delta p will be the change in the velocity of the number 2 mass. It comes in with a velocity v_in and goes out with a velocity v_fin. Okay? But we're saying at first that there isn't going to be all that much difference each time this collision occurs. We're taking a limit where this thing is really tiny compared to this. Almost good enough to have 1 to 49, but the simulations that we'll put up here will be more like 1 to 100 or 1 to 500 for studying this kind of theory. Anyway, this is the change in momentum. And of course, Vn, you see, is negative, right? Fin is positive, you see, so this is a really large negative quantity, roughly twice these quantities, right? Because these two speeds are going to be very similar if this thing isn't moving very fast compared to this. So a lot of approximations here to make this thing work for us, but that pretty well says it. So we have here a relationship between the inverse delta t, just turn this equation over, okay, this one right here, and that is what we're dealing with. Now, momentum per bang times bangs per second is going to be basically the momentum per second that's changing hands here. Now, I remind you of the situation that's true in our double bang sequences when M1, which was 49 in that first example, and M2, which we take to be 1 most of the discussions, the numerical discussions here. This is the situation that occurred when we had the infinite limit on our collisions. And just to refresh your memory, recall this graph right here. We were working with 7-to-1 slope for the pin in the Super Bowl. We took just very quickly something that had a slope of 16, just to make an example. It was between the Super Bowl pin collision final velocity and what you'd get for our case here, which is infinite ratio M1 over M2. So in this case, in a plot of V1 versus V2, the slope is approaching infinity, very large. As I say, 500 is going to be very large for the actual movies that we make of this. But that's equivalent to using a really skinny, tall, skinny this way, tall, wide this way, energy ellipse. M1 much, much, much greater than M2. Here, remember that the square root of the mass ratio is what tells you about the ellipse A versus B ratio. So this is not too far from a 500 case that I'll be talking about. In any case, the result of that, and this is our usual way of doing our collisions. Remember, we start over here with two masses coming down with -1 coordinate for D1 and D2. We had a floor bounce, so this was our really initial velocity in our collision experiment, okay? And then we went up a momentum conservation line to the perfectly elastic point that was balancing the initial with the final off of this 45-degree line. And if the slope ratio of M1 to M2 is approaching infinity, then this is the same thing that's on the blackboard for the infinite case. And you can see that the speed increase is by approximately, and the approximation gets better and better as you get closer and closer to really large mass ratio M1 to M2. This increase of velocity is by twice whatever the velocity is, whatever this is scaled to be. You go up by 2. And when you do it again, you see, if you bounce off the ceiling, you see, bouncing off the ceiling puts you back down here. Okay, you have to now do a bounce from this point here, okay, and then do it again. Just go up the same momentum line with a new balance point, which is up here, again, increasing by twice V1. Okay, so this is what's happening to V2 as we close in on it with M1. Okay, and it will be this sort of relationship that describes the entire sequence of collisions. So the idea of the speed final being the initial speed plus 2v1 each time we have a collision, that's going to be the case, you see. So we're going to be talking about hundreds of collisions, well, lots of collisions, just as we were here, except this could go on for a long time. before we got to the top. And then it's still going to be the same rule coming back down the other side. So that's the basic set of, you might call them differential equations, but they're finite differences, deltas, as opposed to delta p as opposed to dp, and delta t as opposed to dt that you use in differential calculus. So we're going to close in on that limit. Now, the idea for M1 much greater than M2, that's our first assumption, and then V fin is the minus Vn minus 2V1, that's what's happening to V2. The relationship between time and velocity over distance is there as well. So what we're doing is we're taking V fin equal to this. This is the actual thing with the signs in it. We're taking that right there for V fin, okay, in our momentum conservation, or momentum accounting that we're doing here. And remember, in our collisions, every time the little ball hits the ceiling, the total momentum of the system changes by basically twice the momentum of that little ball hitting the thing that's connected to the earth, the ceiling that's connected to the earth. Okay, so what we're having here is M2V n, and then minus M2V and that's plus, so we got 2 M2Vn plus 2 M2V1. So that's the change in momentum that we'll be dealing with. Now, as I say, we're going to be assuming that this big guy, the M1 in this collision, let's put the picture of the thing up here, right up to the point where it is still there. We're assuming as this moves at the kinetic speeds, which are thousands of kilometers per second at room temperature for nitrogen and oxygen molecules, that is very, very large compared to the drift velocity of the monster mass, M1. So we're going to assume a slow monster mass and take V1 out of this equation altogether. So this 2 times velocity of number 2, in other words, the momentum change, 2m2 v2 is going to be the main part of this relationship. So delta p over delta t, this nearly equal to 2mv2, and here we have 1 over delta t. This is our timing thing, v2 over 2y. Okay. This boils down to a force that is inversely proportional to the space y allowed for the m2 at this particular moment. Now that can change, obviously, over a long time, even with slow velocity at m1. So we will be considering that case. But you see, the key thing here is that we're asking for conservation of energy of this entire system. That's called the adiabatic limit. It doesn't sound like it should be called that. Adiabatic means sudden. The reason it is because for large velocity, large volumes, it's really hard to get the energy out of a real system. So if you push the piston in fairly rapidly, not too rapidly to ruin our little approximation, but still rapidly enough that the energy doesn't change, that the walls don't take energy away from this hot object, you let it stay hot, then you have an adiabatic law, and that's what we have here, a force that's inversely proportional to y, but also proportional to the kinetic energy of m2, right there. Okay? So it's 2 times the kinetic energy of m2 is the coefficient of a force law that depends on the coordinate, the main coordinate, the big coordinate of the big mass. All right. So bringing all of that up here, we have a force law that's like that. Now, if I can assume that this is another force law, this is the isothermal force law, assume that V2 is constant for no matter what distance you have. You always move this thing in slow enough so that the walls can take some energy from that object, M2. So we keep the kinetic energy of V2 constant. If that's the case, you have a constant here, then it really is a inverse distant force law. Okay? So that is the basic idea here. Now, we're going to try for getting a better law that describes the situation that really occurs if this system, the whole system, conserves its energy. If we have the perfectly insulating walls, which we use thermodynamic terminology, so that the walls don't heat up this mass when the mass gets too slow, or slow it down when it gets too hot, and thereby keeping it more or less in equilibrium with the surroundings. That's the situation for this law. But for the adiabatic case, we need some more work. And surprisingly, the result is a force field like this. This is quite remarkable, I think. Inverse y cubed, if you really do conserve the energy in this system. I make an analogy of system with the Federal Reserve and the economy. When the economy heats up, the Federal Reserve is supposed to cool it by various monetary or fiscal, obviously monetary for the Federal Reserve, but monetary and fiscal for the entire government. And the vice versa when it gets too cold, like it did in, right at the end of the Bush administration, and we had a major crash. And that the Federal Reserve is still pumping money into the economy to keep things going. And that appears to be something that you actually should do. And Europe didn't do it, Japan didn't do it, and they continued to be more depressed. So who knows? Read Mr. Krugman's ideas about this if you want to see the point. You know, an analogy for this isothermal thing. The conservative economists are taking a view that's more like the conservation of money view of things, and that's what we're going to do here. Now, the idea is that the ceiling is elastic. V2 isn't constant. If M1 changes the distance allowed, the radius y here starts to move in. Well, we know what happens. It's going to make it hotter. And the idea is to take the little coordinate. I'm going to use y1 as the coordinate here. That will be the total height here minus y. This little y1 here is this will be height. Remember, it used to be vertical. Minus that coordinate that we've been using here. So they're linearly related. But the rate of change of y1, or minus big Y, I'm taking y1 this way, which is kind of minus when we turn the thing horizontally, and y1 is a minus y. So got a minus sign here for our time derivative of the y coordinate. Whether we use this one or this one, measured from the origin on the left of this coordinate system, that's our velocity 1. And we're going to let those things vary now. When m1 collides with m2, it adds twice its velocity to v1 to v2. This is the limit of having the mass ratios very different. And this occurs at a bang rate, which we've already talked about, which is the speed of v2 at this moment, divided by the total distance 2y separating the wall and the big M1. Okay, so we have a dv2 there, dv2, v sub 2, with respect to time, that's equal to this 2v1 times the bang rate. And the bang rate v2 over 2y gives you that. And we can also write that. We have a 2y here. We have 2v1. We have a v1, v2. Let's see if that's where we are going here. We have a bang rate v2 over 2y. So here's a 2v1. I can also write that as minus 2 dy dt. This relationship. Okay, I think that makes sense. Now, this is a differential equation that we can solve fairly easily. I'm just going to use the standard integral of 1 over x, good old logarithm, the famous log base e. We're going to have a lot to say about this relation later on, but let's just proceed with this. I have a differential equation here, dv sub 2 divided by v sub 2 is equal to dy over y. That's what results here if I just take away the dt, basically. This integrates to a logarithm of v2 is minus a logarithm of y plus some constant. Or another way to say it is logarithm of v2 is equal to logarithm of constant over y1. This is the logarithmic property. And then we have our v2 is equal to a constant over y. Okay? Same as that, huh? That's interesting. Okay. This is what is going to result, Fauch's law for this thing that results from having that is this rather amusing thing here. I'm just putting in the actual value of v2 squared that we're getting out of this thing. And you see what's happening is we make the force much sharper, not just a constant over y, but if the velocity 2 is going to change, that's what you're going to get. Now, if you, if the y, this is y at t equals 0, you see, and then y cubed, then the idea is that this would give you the force law all the way along. As this thing gets as hot as it wants to get, and nothing's going to take anything away from it, so you won't have a simple thing like this. You end up with a very sharp force law because it's so much hotter than was allowed here. Here we always kept it this v2 equal to a constant. So that's kind of an interesting thing. Now this is the one we're going to use in the simulation effectively. We're just letting the simulation go without letting the energy change. So that's the correct one. If you we don't have a simulation yet that acts like the Federal Reserve, but basically every time the mass would come, I would have a program line that would say, "Hey, are you too fast? I'm going to take it away. I'm going to make you, this one speed v2. I want you to keep constant." And that might be an interesting simulation. It would be pretty easy to do. So let's make a note to do that. Now that we have our so much computing power available. So I want to look at not just the force field, but the potential field, because basically you want to keep track of the energy as it flows out of M1 into M2 and not anywhere else. The box is insulating. The box is not adding or subtracting energy from M2. And M1 isn't hitting the walls at all for most of what we'll be doing here. So I want to show you how we have really two definitions of force versus potential. The physicist definition and the mathematician's definition simply differ by a sign, and you need to see that. It's one more sign to make this sort of stuff confusing. And while we're at it, after we get done with that, we'll check that everything works and is consistent. We'll come back and look at the isothermal potential. The potential for it is the logarithm of y. So we have to derive this. Once we've derived this and made sense out of this, then this follows simply by the integral of 1 over y. Okay, so here's the deal. Big mass M1 feeling potential field or gradient due to a small little guy rapidly bouncing between the object and an insulating wall. And it's the adiabatic case where V2 is some constant over y. Total energy E is strictly conserved. This is what we're saying. We're saying that what we said before, we proved this in the time reversal case. And you see that's the rub here, is that the insulating walls, once they start to leak, that's what we call irreversible. That's what we call entropy. That's what we call time getting an arrow. It's a direction now that you can't tell. You can now tell the difference between the time directions of a movie taken of these scenarios. But without that, with time reversal symmetry, that's all that's going on here. It's just that we replace this with that. Okay, so here's the kinetic energy, and here's what we're calling the potential energy. So once we've proved that energy conservation due to momentum conservation and time reversal symmetry, we then have a kinetic and potential part to our total energy. So what we really saying is big mass M has its kinetic energy. It's the only thing I'm going to track in any energy. Everything else I'm going to call potential. And that should be a constant, the sum of those. So this is where we start the most mechanics classes. We just say, let that be. But I thought you'd be amused to see a way to let it be proved. Okay, this is the reasoning behind that. Now, admittedly, it's only one dimension, but how far can you go? That's the question. Yes?
In traditional approach, I don't remember we define any potential energy for in collisions.
Define the potential energy for?
I mean, in old approach, in differential equation approach, I don't remember any potential energy for collisions. Just considered kinetic energy and momentum and solved the problem. And no potential energy.
It depends on where you start. I think what you're thinking is that somebody gives you a potential for something like a Coulomb or an oscillator, or those are the famous ones that we're going to spend a lot of time on, but this one is another one that's not so famous that we're getting here. And you're given that, and then you proceed to just, as they say at Georgia Tech, plug and chud, right? You solve your equations of motion based on knowing that this either Lagrangian or Hamiltonian has such and such value, and you get an equation of motion. We'll do plenty of that, but right now I'm just saying let's come at it from a point of view of this system where we already know how to solve this system with bouncy little matrices and whatnot, let's see how it would, you know, if you were to treat it the standard way. And now we have a potential for it. We have a potential for two extremes. The adiabatic one that I've colored in red here, and then the isothermal one where you make sure that the energy of the thing that's giving you the force is not changing. I don't know if that answers what you were asking. If you could rephrase, I don't know what it was that you're trying to get at, maybe.
Oh, no, I think he was asking me like when we discuss collisions.
Do a collision.
A problem, when we discuss a collision problem. the
Okay,
standard-
scattering problem of some kind.
Yeah, the conventional treatment, in the conventional treatment, we don't include potential energy. We just say that two objects collide, we just deal with
And-
conservation of kinetic energy and momentum.
That's right.
So he
You
really
assume the
wants-
conservation
Yeah,
of momentum and energy,
and
we'll do some more multi-dimensional ones of those things
Yes.
later
so
on.
I think his question is why, in what kind of problems we include the potential energy.
Well, let me answer that one. Basically, what you're asking is, what do I need the potential for in a collision problem, right? Well, remember that we idealized our collisions right from the first day by saying that these two objects and the wall were separated, and there was never a situation where the wall and the two balls were in contact, right, at one moment, right? Now, in chapter 8, I believe it is, we show what's going on there. In other words, why was it possible for me to get a very accurate result for an actual experiment in this room that involved a brass pen, a ball, right, that was Bali's case, in which the ball lost its energy completely to the pen. How were we lucky enough to get the right answer for that? Because you see, our independent collision model is that there should be a gap between those, right? And when there is a gap, and you can just consider each collision in turn, or when you have a sphere touching a sphere, which has really a very nice potential field or potential force law, so that each of those collisions that occurs down the line completes itself before the next one happens. That's what's really happening here. If that doesn't happen, then it doesn't quite work, and as you can see, it doesn't quite happen, it doesn't quite work. Right now they're sort of randomized, right? So, in order to solve a difficult problem like that, to really get the right answer, we're going to need a potential as a function of distance. The force and trading between three bodies is not something we can do by just simple conservation law. Because we don't know, we know it when we have two, you see, but if we have two and then another one is in there taking how much, we don't know. It depends on how strong its potential or force is compared to the other one. And it depends on how nonlinear it is, as we'll find out. We got to do what we did. Nature was kind to us because of incredible nonlinearity of these force laws. You make them linear, that effect goes away, and we'll show that.
Can you explain the last statement when you say the force laws are nonlinear, but we linearize them for our purposes? So
Yes, I will. It's a little early, but it's worthwhile saying it twice. The most famous force laws, F of y, are Hooke's law,
right, yeah.
okay? That's F equal to a spring constant times y, okay? Let's make the spring constant 1, all right? That's the most famous, right? Sometimes you get a force law that's quadratic, nice parabola coming up here, right? And let's make a constant 1, so this is 1.0 right there, Okay? Then you might go further and say, I'd like to do y cubed. So there's y squared, there's y cubed, and maybe even y4. I'm exaggerating here to make clarity, okay? And maybe y to the 100th power, which would go out here and go boom, right? It's fun to plot these functions just to see what they look like. I mean, that's one of the advantages of computers. You can look at those things. But what you see with these high-powered force laws, these very nonlinear ones that are off of the line, is that you have a flat region. And that's our gap. That's how we get to do our Super Bowl stuff and have it work very precisely.
So which means you approximate the force law
As
with the
having
linear-
zero
Okay.
for a short distance.
Okay.
Now, admittedly, it's a very short distance here. Less than 1,000th of an inch. Fractions of 10,000ths, actually. But it's enough, because these collisions are really fast at transferring momentum. So that is, part of our idealization was very fortuitous. And a collision system like that has a very high-powered force law, which we will calculate. That's a Sagadal theorem that I was showing to you in the next chapter. We'll talk about that next time.
So
Yeah.
for a short distance, for a very short range, when force is zero, it means that the potential is constant, right? For that range.
Oh, that's correct. Yeah, because
So-
as we'll see, the
so
potential
is that the reason why?
is the integral of force.
Yeah. So since the potential is constant, is that the reason why we ignore it? Because a constant term is going to be added
That's
on
right.
both sides of the
Nothing
expression.
is being transferred.
Okay.
They're just doing their maintaining their momentum
Okay.
to get closer, and when they get closer, boom, right? Then it does change,
Okay.
right?
So since the
But by that time, the other collision is finished. So we can do a three-body, what looks like a 3 or 4 or 5 or 6-body thing using independent collision model. We don't need potential. In most scattering problems, they try to get that situation. At least you'd hope for it. It makes it possible to do everything we do by ruler and compass. Maybe that answers what you were after. So now we're going to actually let these, let a potential show its stuff, so to speak, but do it with collisions. The collisions we'll still be using in the background conservation of momentum and conservation of energy to get all of our answers. But then we'll see if we get the right answer by doing it by the ordinary way of the force law. Okay. The thing I'm making a point of here is that this potential energy relates force through work relations. The force, the change in the potential energy, if there's any change in the energy of our potential creating object, which is M2, okay, it's going to be done with a work relation. So the idea is that maybe that's another axiom, and I would say no, it's not another axiom. You can prove it. Okay, if I do an integral of f dy, that's the force is the rate of change of momentum with respect to time, and then y is my major coordinate of distance between these this object that's being tracked and some origin wall that contains M2. I can write that as dy dt, take the dy here, dp there. Okay, it's a calculus trick we can do anywhere that's continuous and differentiable. Okay, and then dy dt, you see, that's the change that we would be actually calling a velocity. Okay, dy dt is the velocity. I mean, plus or minus. We take different coordinates up there. okay? And so that velocity dp, okay, now p is mv, so then you end up with an integral of v dv times m, which is v squared over 2.
First you have integral dp over dt dot dy.
Say again?
First you have on the right hand side integral dp over dt dot dy, dotted with dy. No, the second term on the right.
Oh,
No.
second term on
Yeah,
Left.
the second
This
term from
time.
left, I'm sorry.
this one?
Yeah,
Yeah,
then the next term you write integral dy over dt dot dp.
right.
So how do you do that? Do you integrate by paths? Or,
You just move the dt over.
like what is the justification for that?
That's a typical calculus thing. Yeah. No, that's definitely right. If there's a total derivative, it doesn't work with partial derivatives or anything like that. It works with that.
Okay, so
That's a calculus identity.
does it have a name? I would like to revise it.
Newton. Yeah, absolutely. Yeah. But that's why I say, not another axiom. I can show I'm talking about energy here.
So if you have a total time derivative, you can operate that time derivative on the other terms.
Mm-hmm.
Is it
Yeah.
true just for time derivation or any derivation?
These things are functions, these things are functions of time, y and t, right? And only t. If you got more variables, this isn't going to work.
Oh,
You got
okay.
chain rules and stuff like that. We'll be doing this for higher dimensions, but it won't be this simple. Yeah, that's a cool step right there. I think this appears, Brad, when you're teaching sophomore physics, do you see this in the sophomore physics books? A real quick way to say you get kinetic energy after you've done a force integral.
Yeah, I mean, they keep they hold that thing over until undergraduate.
Okay,
That's in Griffiths too.
okay.
But
Griffith's a more advanced book.
but
Yeah.
freshman physics define this to be work energy theorem. They state work energy theorem this way, like integral
Right.
f dot
Which
dx.
is equivalent to having another axiom. Yeah, you just say it, right? But this is a doorway to it. This is wormhole to it.
Well, is it another axiom?
Pardon?
How is it another axiom?
What I'm saying is this is provable. Once you've decided what that means, the change in kinetic energy is f dy. Normally you'd take that as an axiom. It's not an axiom. This is the result. F dy is this, and this gives you kinetic energy. So there's the U. That's the idea. That's all I need.
Did we already do it the other way?
Pardon?
Because
Yeah, you can go
usually
backwards.
you see it in the differential.
Yeah. I kind of like going this way, just to comb the coconut backwards.
Change the dx and the dy.
The fundamental theorem of calculus is, you do it both ways.
Yeah. That's right. Yeah, no, that's really what it is. It's a mathematical identity, not dependent on your thing. So, rewriting this is a differential way to say f dy, that's the thing we're talking about here, dt. Now it's pretty obvious that I can rewrite that dp dt and then v. That is the derivative of momentum dt dot v, okay? That's the same as the derivative of mv squared over 2 dt, which is the differential of the potential, which is the differential of the kinetic energy of the thing that's making the potential. So while this looks tricky, this doesn't. So this is the second, I say or else, this is nicer way to say it. Which essentially proves that Newton's identity right there. Assuming it's continuous and differentiable. If it's not, you've got to play games. All right. let's go ahead and put this back right now and put the other screen up here with all that stuff. So we've already come through this thing, making what are effectively Boyle's laws for one dimension. Kinetic energy times 2 over a distance is the thing that's responsible for the force, but we call it the isothermal law when we make that kinetic energy of the producer of the force field, V2, of mass M2, a constant. But then we go ahead and allow that energy to change, as it will when you make it hotter, and you get these new rules here. Okay. Just to review a little bit of what we've been through here. Now, the physicist versus the mathematician. You probably aren't aware, but there was a divorce. Once a happy marriage in the Newtonian time between people that worked in the natural sciences and the people that were developing geometry, algebra. Along comes Newton, calculus. Certainly you could say Newton was a mathematician and a physicist, and they didn't have names, they didn't have labels. Then things got complicated, and now we have separate departments for mathematics and physics. And different viewpoints, and different, it gets to the point where the two can't even talk to each other at high level. Very few physicists in this department really even know the first thing about group representation theory, for example. It's just glorified Fourier analysis. They don't know that very well either. So they're not conversant with the applications, mathematical applications, that are so beneficial for making use of the sort of, shall we call it, finite mathematics, the mathematics of groups and algebras. Now, when it comes to actually treating the force law, you could say that the physicist's view of the force imagines that this M1 that we've been talking about being a victim of an M2 behind the scenes. This behind the scene M2 produces for us a potential energy that depends on where M1 is. If M1 is very close to Y, then the potential is high, because then M2 is really going at it, right? And nobody's taking the energy away from M2, so at this moment, this mass will be sitting here higher in energy. That's because it's in a higher potential, but more importantly, it's sitting on a steeper slope. So the actual force that wants to make it go is given proportional to the derivative of that function. This coming from our basic idea, f dy equal change in this energy right here. This particular one is a function of constant times 1 over y squared. So it blows up according to a quadratic of that distance, y, as it goes to 0. So the geometry is that the delta u and the delta y sit on the altitude and the base of a triangle that is tangent to this curve, you see. But with a minus sign, and that's important. So this is the make it go force, the force that causes things to go.
In this case, on the plot, the plot on the left-hand side, this one, yeah, that one.
Yeah.
The slope is negative, right? Because so have you put a minus sign just to make the derivative positive?
Well, the force. Remember, we changed our signs a little bit here. I guess I don't see it here right now, maybe down here, yeah. Remember, this is the y that goes this way, right? And it's h minus that y. So, yeah, sure, I should have drawn it around the other way so that when this derivative right here takes on a negative value, it would be a negative force. Right now, that derivative is negative. In order to get a positive force, I have to put a minus sign here to make it go where it's supposed to go, right? So I would encourage you to stay being a physicist. This is a definition that you should live with in this building. But in chapter 10 of the review, where we do complex variables, and we define complex potentials and complex force fields, okay? This minus sign is a pain in the ass. It's much better not to have it. And that's indeed what potential theory, developed by very pure mathematicians, Cauchy, well, my memory fails me at this point, the conformal geometry, and all the stuff that comes out of complex variables, which we're going to review very physically, it's really much nicer not to have a minus. We've got enough minus signs to worry about.
Residue theory?
Pardon?
Residue theory?
That's Cauchy.
Yep.
And there's the Riemann-Cauchy relations. We're going to go through all of that stuff in a very physical way without having minus signs to bother us. And the mathematician's view of force that does that is that this is the force that you need to apply to hold it there. I mean, after all, Newton's third law says if you give something momentum, well, it's got to take it, right? That means something that's giving it is losing momentum and energy, and what's taking it is just the opposite sign. So this is just the third law here. There's an equal and opposite force for every possible description. And you might as well write down the mathematician's force as that force which would hold this thing here. And they were talking about charges in fields. They were thinking about that while they were making that particular application of complex variables. So the idea of holding a charge somewhere, how much force does it take to hold it there, was very natural, you see. So that is the difference. The physicist force, and it looks like I've got here an equation like this. I should have had math there. It's a typo. Every sign has to change in these relations.
On the diagram on the right side, on the right hand side, the mathematician's view of force, even in this figure on the right, the slope is going to be negative, right?
The
The
derivative of that curve is very negative,
Yeah.
right? And the mathematician's force, mathematician would say you have to apply a negative force to hold it there.
Okay.
To hold it there. This is the force to hold. That's the other way to say F math. Okay? This is the force to go.
Okay.
Would they actually take it even one step further, divorce themselves of mass 1 altogether, and consider a gradient of a potential?
Well, then there's the gradient. You'd still either put a minus sign on the gradient, or you'd put a plus sign on the gradient. Now, when we do that chapter 10 stuff, we're always going to put a plus sign. We'll have a force field F, the derivative of it with respect to Z, okay, with a plus sign, you see, will be the force. This will be the phi, that will be the F. And vice versa when you write it as a derivative. I will use that convention then. Okay? Now, the question is, does it work? Before we talk about whether this makes sense with what we've written down here for the potentials, you see, does it give the force that we got? Okay, I want to remind you of what may be the source of the term, constipated mathematician, because they're holding back the physicist lets the shit go, right?
Sometimes they even throw them. They even throw the things.
Exactly, exactly. So yeah, all three of these guys are all tiny. Anyway, that's a mnemonic that will let you remember what the sign is. Here's the physicist force.
Wait, can we go back to the definition? What was our definition of potential?
The definition, don't forget that, is, thank you, Brett, the definition of a potential is the kinetic energy of that little dingleberry, whatever, the M2 that's causing the force. And remember, we're talking about big M feeling a force and getting turned around, and it's going to follow a trajectory and do all kinds of things later on.
Is that the standard definition?
Not standard. This is not standard.
Okay.
But this is making a point that all potentials are ultimately due to kinetics of some kind.
That's why I was like, is that one?
Potential is just sort of a bookkeeping technique that works if you don't go too fast. It starts to fall apart already in atomic physics. It's pretty good for molecules. There's very little people argue about it. If you have a molecular potential, you can get 12-figure accuracy in spectra if you really had that potential right. Maybe I'm exaggerating a little bit, but I know of first principles calculations that claim at least 10-figure accuracy. And the experiment is much better than that, so these are things we can check. So I would say that that's a, potentials are fine down to the molecular level. And they're certainly just fine talking about things that are flying around, spacecraft and most of the electrostatics that you do in vacuum tubes and things like that. But when you start to get down to the atomic level, it's starting to go to pieces because you don't really know where things are and stuff like that. There's waves. And nuclear physics, very seldom do the potentials work. In high energy physics, forget about it. They don't have potentials. So you really start pumping up the energy, can't play this game. But for most of the physics we do, and certainly all of classical mechanics, potential is absolutely 50% of the story most of the time, maybe even more.
Dr. Harter,
Yes.
when you say at high energy physics there is no potential, that's because the particles are moving at high speeds, right? Close to.
That's part of it. But you see, we understood that this thing really works when it's adiabatic, right? There's not something else that can take it away.
Right.
You see. And also we got to know where things are. Now, if you get down to things where you're moving M2 fast enough, right, that M1 fast enough that M2 can't keep up, forget about it here, right? We made the assumption in the beginning that M1 was moving slowly compared to M2, okay? But anyway, the answer to this question is, does it work? Is hurrah, it certainly does. If that's the thing that we came up with, remember the y cubed with the constant squared? Forget about what the constant was right now, okay? If you can forget that, if this force is this, and that's the force law that we came up with. So, let's see if we've got, did I make another, no, they agree, okay? I take a derivative with respect to y of this thing. That's the key thing that we're working with here, this potential right here. And I take a derivative of that, and I get, I need the 1/2 in there. Once that comes in, it gives me exactly this force. So, yes, it does. It works fine. And it will work for isothermal, too. Okay? Now, I take isothermal as an example because I can forget about the velocities and I just have a first power. Of course, I pay for that first power by having its integral be a logarithm, so that's a little annoying. So we're going to have logarithm curves here, and if I'm getting hit from two sides, and that's what I want to show, and we'll be showing a movie of that very shortly here. So go ahead and you're welcome to get it set up.
It's ready.
But you see, what's cool about it is you have a logarithm that's on this side repelling it on this side, and then you have another logarithm that's turned around repelling it on that side. The sum of those two is a very nice, not a fancy function like that, but essentially a parabola. At least in this region. This is a, what you get f of 1 over 1 plus x, okay? That's this distance right here, and then you get 1 minus x, turn the other way for this one, okay? So it's these two together, okay? Now 1 over 1 plus x, that's an easy to remember binomial expansion. 1 minus x, even easier to remember, it's just the sum of all the powers, okay? And then you subtract those two, and to second order it is, third order it's wrong, but to second order it's just minus 2 f dot x. This is a harmonic oscillator. That's cool. I can make a harmonic oscillator out of two little particles that go really fast, and the m will supposedly follow. Well, we'll be doing lots with a harmonic oscillator. Just to remind you from freshman physics, if you have a harmonic oscillator, it has a spring constant K, Hooke's law, okay? We already mentioned Hooke's law here. It would just be pointed the other way with a minus sign. But this is the mathematician's Hooke's law with a plus sign. And I take these two and I get that, okay? In any case, with just that and not the extra terms, this thing has one frequency of oscillation, and it's a sine curve, cosine curve, trigonometric things that we'll spend a lot of time in the entering chapters of the review and later in Unit 4 talking about. Now, that's the thing I'd like you to see. Go ahead and cue that one up, because this is really quite surprising. Now, he has it turned to an extreme case. I also have a slide here that has this one in it. Go ahead and show where it's located.
Control panels.
When you go to the control panel, you have to go way down.
This is what you get when you launch it. It goes into the default, and then you have the control panels. And there are several scenarios located at the middle level here are these ones that we just
We've already done a lot of those. And you're going to pick the 500?
500 to 1, and you can
Yeah,
tell
yeah.
by looking up in the top
So
left corner.
yeah, it's 0.1 whatever units you want to use, 50 units, right? Is that what you've got?
Mm-hmm.
Okay, go ahead. Except that he's got, let's see, 0.150, same as this, but he's got the scale turned up, speed turned up, so that you get a really sharp sine curve. And you can see the sine curve and the turnaround points for M2 on their movie. You can see it here too. It's just a little harder to spot because it's so fine. But there is a pretty nice sine curve being made. Isn't that cool? The spring of bumps. Just bumping. That's all that's going on here. Just bumping. And we're getting a pretty smooth sine curve. We started the initial conditions with just the right velocity. If you set the velocity to 0, it wouldn't do anything. So what he's looking at is this one. I think this is pretty close to it. This one actually shows the settings for that particular one. This is not quite as fine as yours, but it is really perfect. And it held the energy pretty well. Now the one he has is, pushing the envelope a little bit. This is the whole, I ran it all the way out, so you didn't have to. Mm-hmm. And here is a line drawn, and you can see it's sagging. There's a little drift to it, okay? And that's because for these particular values, the energy changed. Here's what the energy started with, 64.052. I don't know what you're starting with your current setting. I think it's the same, okay? And the energy up here is all the way up to 63.9, or down to 63.9. So it's lost energy. That means that the integration procedures are not giving us solid. That's why we put the energy in here to check. You're running it too fast. You've got to give it more time to go through the bounces. And as a result, because of that, back again, because of that, this actually sagged. And I think if you ran yours out, but you can't see it unless you draw a line. You have to take this thing out, draw a line out.
I didn't see that first pass.
Yeah.
The other scenarios exhibited a lot to a greater degree. You can see it by eye for sure.
Yeah, as you start to make the masses more equal and various other things, finally you get a chaotic system. But this is very well a thing. Now I'm going to ask you as a problem, this is in fact the adiabatic case. The thing that I was showing you the math for, the algebra for, just a second ago, this is just simply isothermal case. I want you to see what's the difference between using this and using the y cubed. I'll be giving that Thursday. Similar to one I gave last year, I'm going to mess around with a little bit, massage it. Okay, so I'd like you to see what's the frequency that you get for certain values of mass, initial velocity. All of those things figure in the frequency of this funny oscillator, this bouncy oscillator. You see, how long a period should I be getting here? I'm getting about 9 seconds. This will be a good, test of the theory, quote unquote, that we've been playing with here today. So I think that shows you pretty much what it is. Now we get crazy, and it's also the end of our time allotted, and we may be also running out of battery in Al's camera here. What is it right now?
We're on our last bar.
Last bar. Okay, well that's good to know. It'll make it through a class, at least now. You know how when you fill those and empty those batteries, they start to lose time. We'll see about that. But in any case, the crazy stuff we'll do at the beginning of Thursday's lecture, and I'll call it a cut at this point. But